Hello and welcome back. Today we're going to continue learning about work. We're going to talk about how to calculate the work that's done by a variable force. So that's a force that's not constant. We're also then going to talk about how to calculate power. So let's first start by reviewing a little bit about what we talked about in class, because this can be a little bit confusing. There are a few situations in which there can be a force applied to an object, but there's no work done. Remember that we said that in order for there to be work done, there has to be a force that's applied, there has to be a displacement of the object, and at least some part of that force has to be in the direction of the displacement. So in a case like this where something's going around a circle, is there any work being done by the centripetal force, the force that's pushing it in toward the center of the circle? The answer is no. Why? It's not because the force doesn't exist. It's not because there's no displacement. It's because the force and the displacement are at a right angle to each other. So they're perpendicular. So there's no component of that force that's in the direction of the motion. Another way to think about this is forces that do work, when work is done on a system, then that changes the energy of the system. It causes it to either speed up if you're doing positive work or slow down if you're doing negative work. Well, in this case, if something's going around a circle, if it's uniform circular motion, right? The very definition of what uniform circular motion was something that is not changing its speed. So it's not changing its speed. That means it's not changing its kinetic energy. So overall, there can be no work done by any of these forces. Another situation in which there's no work done is in the case where, like this situation of the roller skater here. So imagine this girl's on roller skates. She pushes off against the wall. How much work does the force that she pushes on the wall, or excuse me, that the wall pushes back on her? Force does, how much work does that force do on her as she pushes? Well, in this case, this is a little bit tricky because she's actually moving, right? As she pushes against the wall, her feet maybe move backwards. So she straightens her arms and pushes off from the wall. So it's tempting to say that that force must be doing some work on her. But remember we said that the point right here where the force is applied, that point has to actually be moving. There has to be displacement of that point where the force is applied in order for there to be work done. So in this case, even though her body as a whole is moving, her center of mass is moving, there's no motion at the point where her hands are touching the wall. So there's no work done by that specific force. The force doesn't push anything through a displacement. So no work is done in that case as well. So a quick question there for you to think about. A car on a level road turns in a quarter circle counterclockwise. We know that static friction causes centripetal acceleration. How much work is done by static friction in this case? The answer here is 0. There's no work done by static friction because the friction force has no component that's in the direction of the displacement. Okay, now let's talk about variable forces. One of the most important variable forces that we're going to deal with is a spring or elastic force. So if you stretch a spring or if you stretch a rubber band, then it tries to pull back to restore it back to its equilibrium length, its unstretched length. When you let it go, it's going to snap back into place. Any kind of system that tries to restore, or any kind of force that tries to restore a system back to an equilibrium position is what we call a restoring force. A spring force is a great example of that. If you push a spring in, it's going to push back out to try to get back to that equilibrium point. If you stretch it, it's going to pull back, try to get back to that equilibrium point. Springs are not the only examples of restoring forces. Another good example is something like a pendulum. In the case of a pendulum, gravity acts as a restoring force because as the pendulum swings up, gravity pulls it back down towards the middle. And every time it swings, gravity constantly pulls it back towards that middle point. But we're not really going to look at that one today. The main one we're going to look at today is spring forces. In a minute, we're going to look at how to calculate the work that's done by a spring force. But first, let's take a step back and just think about how to actually calculate the force exerted by a spring. So we know the direction the force will be exerted. If you compress the spring, then the force provided by it is going to be opposite the displacement. There's actually a direct relationship between the amount that you stretch it and the force that is exerted by the spring. And that force increases the more you stretch it. So it only takes a little bit of force to stretch it a little bit. But as you stretch it more and more and more, it takes more and more and more force, and it exerts more and more and more force back on you. So this relationship between the displacement of the spring and the force was first discovered by a scientist named Robert Hooke, who lived in the same time as Isaac Newton, although they were not friends. They were in fact mortal enemies and wrote many horrible letters back and forth to each other, which is a whole very interesting story, but we won't get into right now. Because Hooke was the one that discovered the relationship, we call it Hooke's Law in honor of him. And Hooke's Law says that the force exerted by a spring is equal to minus this constant called K times delta S. So the constant K is called the spring constant, and it's usually measured in units of newtons per meter. Sometimes newtons per millimeter. You could have other units as well, but primarily we have newtons per meter because it tells you how many newtons of force you get for every meter that you stretch it. So delta S is the displacement from equilibrium. Now we have to be careful that we have the right signs for delta S. This negative sign right here in Hooke's law is there because it tells you that the force is always exerted opposite to the side, which way you displace it. So if we stretch the spring, here we show that, we pull the spring out this way, that is a positive displacement, positive delta S. That means that the force exerted will be back this way, right? A negative force for a positive displacement. If you compress the spring in, we have a negative delta S in that case, and that gives us a positive force because the force is going to push back out. So let's look at an example of just calculating how much force will be exerted by a spring. In this case, we have a spring that's used to attach to a train and used to pull a 2-kilogram block. The other end of the spring is attached, like I said, to the train. The train moves forward at 5 centimeters per second. The spring constant is 50 newtons per meter, and we know that the coefficient of static friction is 0.6. So write down that K is 50 newtons per meter. Our our coefficient of friction is 0.6. And we want to know at which point does the block actually begin to slip? How long is it going to take until the block slips? Because eventually the spring is going to exert enough force to pull it. So the first thing we want to do is start with drawing a free body diagram. It's always a good place to start. If you don't know what else to do, you're never going to go wrong by starting with a free body diagram and identifying what forces are acting on the block. In this case, we would have 4 forces. In the up and down direction, we have the normal force acting up, we have the force of gravity acting down. To the right, we have the spring force, and to the left, we have the static friction force. Now think about what happens just before the block begins to slip. As the train moves forward, the spring is stretched more and more because initially the block doesn't slip, so it stays in place. So you're stretching the spring more and more, so the spring force over here is getting bigger and bigger. Well, what happens to the static friction force in response? The static friction force also increases. It keeps increasing, increasing, increasing to balance out the force that the spring is pulling on the block. But there's a maximum. Eventually, you reach the maximum static friction force. Remember, we know that the maximum static friction force will occur where it will be equal to the coefficient of static friction times the normal force that acts on the block. So at that point, right when it first starts to slip, that means that the static friction force will have to exactly be equal to the force that the spring exerts. When the spring force becomes just a little bit bigger, then it's going to slide. So that's right at the moment before it starts to slip, they're going to have to be equal to each other because at that moment, you're going to have your maximum force. Friction force cannot get any bigger than that. So we know that the static friction force has to equal the spring force, and we know that the spring force is equal to K times delta X. So we'll write that out. I'll write that again over here. Now, how do we calculate the static friction force and the spring force? Well, we know that the friction force, the maximum, is equal to mu s times the normal force. We know that the spring force is equal to k times the displacement. We have to be kind of careful here about the signs, because if you remember Hooke's law earlier, we said it's minus k times delta x, and it is. The minus sign is there to help you figure out what direction the force will be exerted. If you stretch the spring, it pulls back. If you compress the spring, it pushes out. But when we're writing it out in a problem like this, we have to think about what direction the force is actually being applied to the block. So remember that we're talking about the block here. So as the spring stretches, which way is the spring exerting a force on the block? The spring is exerting a force on the block that way. So when we use spring force in our equations here, we just want to use the magnitude of the spring force because we already know that it's pulling in that direction. So we wouldn't have to put another negative sign in here. Okay, once we have this then, what do we know what the normal force is equal to? Well, in the y direction, we only have two forces, and there's no acceleration in that direction either. So we know that the normal force has to be equal to the weight of the object. So over here we would have mu s times mg equals k times delta x. We can use this to solve for this delta x. What is the distance at which it starts to slide? And if we know the distance, then we can work backwards from that and figure out, okay, how long did it take for the train to go that distance? So as I just showed in the previous slide, we can solve delta x, solve that equation for delta x, and get that delta x is coefficient of friction times mg divided by k, which gives us a distance of 0.235 meters or 23.5 centimeters. And finally, how long does it take to go that distance? Well, we know that the speed of the object is equal to the change in position over the change in time. So therefore, the change in time will be equal to the change in position divided by the speed, which is going to give us 4.7 seconds. Now that we know how to calculate the force exerted by a spring, now let's look at how to calculate the work done by the spring. In general, to calculate the work done by any variable force, we can integrate the force times the displacement if the force is changing in time. Now in practice, how this is normally done is by finding the area under the force versus position graph. So it's telling you how much total work is done. If you have a function, then you can actually do the integration, but often you just have a graph. And this works for any type of variable force that's not constant. So let's look at an example of that. In this case, we want to figure out how fast will the car be traveling after it goes the 200 meters shown. We know that the work done has to equal the total change in energy of the car. In this case, we only have one kind of energy that we have dealt with so far. So that means that the total work done has to equal the change in kinetic energy, which is 1/2 mvf squared minus 1/2 mvi squared. Vi is 0 because then it starts at rest. So if we know the work done, then we can calculate the final speed. So next, let's think about what forces do we actually have acting on the car. Well, we have three that we know of in this situation, right? We have, I'll draw a picture up here. We have the weight, we have the normal force, or the tension force. Now there might be some friction force, likely there would be, but we don't know anything about that. So we're going to ignore friction for now and say that friction is negligible. Do we have to calculate the work done by all three of these forces? No. Why not? The normal force and gravity don't do any work because the displacement of the car is in this direction, in the same direction as the tension. So there's no work done by normal and gravity, so we can totally ignore those. We really only have to find the work done by the tension force. How do we find the work done by the tension force? Well, we can't find the work in the normal way because it's not a constant force. So we can't just say force times displacement because what force would we use? Do we use 5,000? Do we use 0? Do we use something in between? What we need to do is we need to find the area, that the work done equals the area under the curve. So the work done here would be the area under this graph, which is 1/2 of 200 meters times 5,000 newtons which is 500,000 joules. So then we can come up here and say, okay, now I know that the tension force does 500,000 joules of work. I know that the mass of the car is 1,500 kilograms. What is the final velocity? Solving this with the final velocity gives you a final velocity of 26 meters per second. Now let's see how to apply this to the specific case of a spring. So we know that we can find the work done by a variable force by integrating or finding the area under the graph. A spring force is a variable force because it depends on the distance. All right. So if we have an equation for the spring force, the force exerted by a spring is equal to minus K times the displacement of the spring. Right? That's Hooke's law. Well, delta S is equal to the final position minus its initial position, which is the equilibrium position, right? We can put that in here and integrate that. You're integrating with respect to S, and we say S because we don't want to call it X or Y because it could be in the X or the Y direction depending on how the spring is oriented. So you can then substitute in X or Y for S depending on what the actual problem is. But if we integrate this, then we get a expression here for the work done by spring, which is minus 1/2 K times the final displacement squared minus 1/2 K times the initial displacement squared. Another kind of variable force that we can talk about is friction forces. Friction forces typically tend to increase the thermal energy of an object. So what exactly is thermal energy? We know that something that has hotter has more thermal energy, but what exactly is thermal energy? Well, thermal energy is a way to measure the average kinetic energy of all of the atoms and molecules inside an object or a system of objects. The total thermal energy really is the sum of kinetic and some potential energy that they might have as well, but primarily kinetic energy. So as things get hotter, the molecules move around more and more and more, therefore they have more thermal energy. How does friction increase the thermal energy? Well, as two objects slide against each other, that interactions between the atoms at the boundary transform kinetic energy into thermal energy. Both of the objects that are sliding past each other therefore get warmer. Those molecular bonds stretch and then break, and then it's transformed into kinetic energy, and the objects move faster. So that energy, although it's still present, it's a form of energy that's very difficult to get back. So it's not a kind of potential energy. We can't turn thermal energy back into regular mechanical kinetic energy very easily. How do we figure out how much energy is, how much thermal energy is created or is transformed in an interaction? Well, that's a little bit difficult. There's not a simple equation that we can use like we can for, say, the work done by a spring or something like that, how much work is done by friction. We have to look at the other forces that are involved. We know that the change in energy of a system equals work, right? And we know that work is equal to force times distance. So usually we can calculate the change, how much thermal energy increases in a system by calculating how much work is done by friction, because friction is the main force that will increase the thermal energy of a system by doing work on it. How much work is done by friction is the friction force times the displacement. So let's look at an example problem of doing just that. So in this case, we have a rope with 30 newtons tension. It pulls a 10-kilogram crate 3 meters across the horizontal floor starting from rest. And the coefficient of friction between the crate and the floor is 0.2. How much does the thermal energy of the system increase? And then what is the crate's final speed? So we have here, once again, 4 forces that act on the crate. We have the weight, we have the normal force, we have the tension force, and we have kinetic friction force as it's being pulled across the floor. This is the force that's going to be increasing the thermal energy. So if we want to find out how much the thermal energy increases first, it's usually equal to the work done by friction. How much work is done by friction here? It's equal to the friction force times the distance that it moves. What's the friction force equal to? Sorry, that should be K. Let me fix that. Friction force is equal to coefficient of friction times the normal force, which we can tell in this case will be equal to the weight times the distance that it moves. It gives us that the total change in thermal energy of the system is 58.8 joules. Now, what's the crate's final speed? Well, which one of these forces is increasing the speed of the crate? That's the tension force, right? So the total work done on the system equals the total change in energy. Well, now we have two ways that energy can change, right? We have the change in kinetic energy plus the change in thermal energy. The last thing that we're going to talk about today is power. So work is how much energy is transferred either into or out of a system. But in many cases, we want to know not just how much energy was transferred, but how quickly that energy was transferred. And that's what power measures. So power is the rate at which energy is transferred. So it's the rate of doing work. The SI unit of power is the watt, which is defined as 1 joule per second. You also often find horsepower still used as a unit of power. 1 horsepower is equal to 746 watts. So here's some examples of power and how we might use it. A lot of times we think of power in terms of electricity. So if we talk about how much power is being used, we're talking about how quickly we're using electricity. For example, a 100-watt light bulb uses energy at a rate of 1,000, well, not 1,000, but 100 joules every second. When energy is transferred by a force doing work, then power is the rate at which we do that work. If a particle moves at a certain velocity while acted on by a force, then the power delivered is equal to the dot product of the force and the velocity, which, as we learned earlier, is F times V times cosine of the angle between them. So let's look at a quick question here. 4 students run up the stairs in the time shown. Which student has the largest power output? I want you to think about this, and then we're going to answer it at the beginning of class tomorrow. Let's finish with a quick example about power. So a factory uses a motor and a cable to drag a 300-kilogram machine to the proper place on the factory floor. What power must the motor supply to drag the machine at a speed of 0.5 meters per second? And we're also given the coefficient of friction. So first think about the fact that because you're pulling on it at a constant speed, you know that the tension force has to equal the friction force. Those two forces have to be in balance, and the friction force is equal to the coefficient of friction times mg. The power output is equal to the force times the speed. They're in the same direction in this case, so there's no angle. So the tension force is mu k times mg. The speed is v. Using all of those values that were given in the problem, we get that the power output of the mower is 882 watts.